So in this session, I will go over very quickly the little bit of trig substitution we did last time, and then go on and we complete the discussion of trigonometric substitution. Okay, so once again, I would suggest trying everything else before you try trig substitution. If the integral can be done by a regular substitution or by parts, then I would suggest not doing a trig substitution. Okay, so for example, if you have something like this, when you have root of 1 minus x squared in your integral, and you've also got an x dx, then I would suggest using the substitution u equals 1 minus x squared instead of a trig substitution. On the other hand, when you don't have a multiple of x dx in the rest of the integral, then okay, we have the possibility of using a trig substitution, and for root of 1 minus x squared, we use the trig identity, starting with cos squared plus sine squared is equal to 1, and then cos of theta is root of 1 minus sine squared theta. So that suggests a substitution of the form x is equal to sine theta. Okay, we saw that last time. What if we generalize this a bit? We have root of a squared minus x squared. Now again, if you have a multiple of x dx in the problem, you might just want to let u equal a squared minus x squared. On the other hand, if you don't, then a trig substitution of the form x is equal to a sine theta might be tried. Okay. Again, we saw that last time. And the other thing that we saw was something of this form, integral 1 over a squared plus x squared dx. You remember that 1 plus tangent squared theta equals secant squared theta. So this suggests something of the form a tangent theta. So you let x equal, all right. One thing that you could try is you could try x is equal to a tangent theta as your substitution. And if you do that, then integral 1 over a squared plus x squared dx becomes 1 over a arctangent of x over a plus c. Okay, and again, there you're using the identity a squared plus a squared tangent squared theta equals a squared secant squared theta. Okay, so that's a brief review of what we did last time. And now we go on with the rest of the discussion of trigonometric substitution. So supposing that you've got this, I equals the integral of the root of twice x minus x squared dx. Okay, so that doesn't remind me of any sort of trig identity. And what I might do instead is, if you've got a quadratic under a root, what you might want to try is completing the square. So if you look at 2x minus x squared, we can write it in an equivalent form, which might be more convenient for us, by completing the square. And so what we do is we say 2x minus x squared. I like to have the square term out in front, so I'll rewrite that as minus of x squared minus twice x. Now if I do completing the square, x minus 1 all squared gives me x squared minus 2x plus 1. So x squared minus 2x is x minus 1 squared, and then that would give me 1 more than what I wanted. Okay, so it's x minus 1 squared minus 1. Okay, now let's use the minus sign, and then you'll get 1 minus x minus 1 squared. Is that algebra okay? Okay, just shout it.
Yes, sir.
Yes?
Yes, sir.
Okay. Now, so let's go back. Let's replace the 2x minus x squared by 1 minus x minus 1 squared. So this gives me my original integral can be rewritten as integral of the root of 1 minus x minus 1 squared dx. Now, what was the integral that we knew how to do? We knew how to do root of 1 minus x squared dx. So this says, how about we try a substitution? We'll let u equal x minus 1, and then du will be dx. So if I let u equal x minus 1, and I let and then du equals dx, then the original integral is the same as I equals the integral of root of 1 minus u squared du. Now what do I do?
Integrate by substitution, I guess.
Yeah, you can do the substitution that we saw before for this form was u equal sine of theta. Okay, so from this point on, you know how to do it. Okay. All right. What about this one? Example 5. You have I is equal to the integral of 1 over x squared. Yeah, Basit has a question.
Yes, sir. Sir, in the last slide, we just changed x minus 1 whole square to u square, and then we changed dx to du, right?
Yeah. Yes.
Okay, so there isn't any dv. Before we were doing u and dv, making.
We're not doing integration by parts. I don't need a dv.
Okay, sir.
Okay. So I is equal to the integral of 1 over x squared plus 2x plus 1 dx. What do you suggest?
I guess make a complete square in the denominator.
Yeah. So what would I get?
Like x squared plus 2x plus 4 minus 4, and then you can just take a bracket and square and then manipulate in a way that you get an expression.
Right.
I guess.
Okay. So I can do this like this. I have integral 1 over 1 plus x plus 1 squared dx, right? So x plus 1 squared is x squared plus 2x plus 1, and then I need another 1 to get my denominator. So this is I equals the integral 1 over 1 plus x plus 1 squared dx. Now, we already know the form integral 1 over 1 plus u squared du, right? That's the one with the arctangent, right? So if I let u equal x plus 1, then x plus 1 squared is u squared, and dx is du. So the integral is the integral of 1 over 1 plus u squared du. And what's that?
So the tan inverse.
Yeah, tan inverse of u plus c. And then remember u equals x plus 1. Your final answer, if the original problem was all in terms of x's and dx's, then your final answer should be in terms of x and dx. Okay. All right. Next one. I is equal to the integral of 1 over the root of a squared plus x squared dx. Now, u equals a squared plus x squared is not going to work, because if you had that, then you would want a multiple of twice x dx in the rest of the integral, but you don't have that. Okay, so that's not going to work, right? A simple substitution. Okay, so let's say that I decide to try trig substitution. Can you suggest what what's the trig identity that I would want to use here?
Sir, A is equal to A sine theta.
Yeah, so I could, the trig identity that I'm thinking, what I would think of would be 1 plus tangent squared theta equals secant squared theta, right? So A squared plus A squared tangent squared theta is equal to A squared secant squared theta. So probably X is equal to A tangent theta is what I want to use. Okay, so once again, the identity that I'm thinking of is A squared plus A squared tangent squared theta equals A squared secant squared theta. So I think of this as my X squared here, right? So X is equal to A tangent theta is what I'm looking for. Right? And if I try that, then, right, then if I let X equal A tangent theta, then A squared plus X squared equals A squared secant squared theta. So then the integral is I equals the integral of 1 over the root of A squared secant squared theta. And since X was equal to A tangent theta, what's dx equal to?
Secant
A
squared
secant
theta.
squared theta.
A secant squared theta. Okay. So now, let's see, I take out the A, and if I simplify everything, I get the integral of secant theta d theta. And what's that integral?
Log tan theta plus sec theta.
Yeah, log of the absolute value of secant theta plus tangent theta plus c. Okay. Now, remember, we want the answer in terms of x. So remember, x was equal to A tangent theta. So what's tangent theta in terms of x?
X over A.
X over A. And secant theta, well, what was secant theta? Secant, remember, right? Remember, 1 plus tangent squared theta is equal to secant squared theta, right? So that means that that's the root of, secant theta is the root of A squared plus X squared over A. So now I replace everything. I replace tangent theta by X over A, and I replace secant theta by root of A squared plus X squared over A. So I now have log of the absolute value of X over A plus a root of A squared plus X squared over A plus C. Everything's being divided by A, which is a constant. So if I want, I can replace that as logarithm of X plus root of A squared plus X squared, absolute of that, plus some other C, let's say C prime. Okay. Any questions about that one? If you wanted to, of course, you could have left it just as this form that we had here. That would be fine. You don't have to simplify it if you don't want to.
Sir, just making sure, C prime in the final answer, that's basically just the regular constant plus a log constant value of A, right?
Yeah, that's right. Okay, how about this one? I equals the integral of X squared over root of A squared minus X squared dx. Okay, so if I'm tempted to use a regular substitution of the form U equals A squared minus X squared, then what I want in the rest of the integral is a constant times minus 2x dx. But I don't have something times x dx. I've got x squared dx. So the U substitution by itself wouldn't solve the problem for me. So again, I might be tempted to do a trig substitution. What substitution might I use here?
Sine theta. A sine theta.
X is equal to A sine theta, right? So remember, once again, we know that A squared minus A squared sine squared theta equals A squared cos squared theta. So I might let X equal sine theta. Okay, so we let X equal sine theta. That means dx is equal to what?
Cos theta.
A cos theta.
Cos theta d theta. Okay. All right, so if I do that, then the top part was x squared. X squared is a squared cos squared theta. And the bottom part is the root of, the top part is a squared sine squared theta. The bottom part is the root of a squared cos squared theta. And dx was a cos theta d theta. Okay, so then after I do some substitution, after I do some simplifications, this gives me the I is equal to the integral of a squared sine squared theta d theta. Okay, how do I evaluate sine squared theta? The integral of sine squared theta?
So we use the double angle identity.
Yeah, that's right. I used the double angle identity. Where did we had that right at the beginning, right? So, where was that? Yeah. Remember we had this identity for cos squared theta is the same as 1/2 cos 2 theta plus 1/2. So there's a similar one for sine squared theta, which you should know, right? If the thing in the round brackets is cos squared theta, then what is sine squared theta?
So how did we get that? 1/2
Double
cos 2
angle
theta
formula.
plus. And what is double angle formula?
Cos of 2 theta is cos squared theta minus sine squared theta.
Okay, got it.
Okay. So sine squared theta is 1 minus cos squared theta, right? So 1 minus this is 1/2 minus 1/2 cos of 2 theta. Okay, and then you have something that's easy to integrate. Okay. Where were we? Okay, so you know how to integrate that one. Okay. So, are there any other questions about this one?
Sir,
Yes.
the sine square theta would become cos square theta minus cos 2 theta, right?
Yeah, it's like 1/2 minus something, right?
But sir, isn't cos 2 theta cos square theta minus sine square theta? So
Yeah,
if we
cos
shift
2
the
theta
other
is
side-
cos squared theta minus sine squared theta.
So if we have to evaluate for sine square theta, we would have to shift the cos square theta on the other side, and it would become cos square theta minus cos 2 theta.
Yeah, something like that, yeah.
But there isn't any half there.
I think you're going to get some halves in there. Yeah. Okay, any other questions?
Sir, could you just go
Sir,
to the
can you
previous slide for
expect-
1 second? Oh, sorry, go ahead.
Previous slide?
Yes, please. Just okay. Right, that's fine. Okay, thank you.
Okay. Right, there was another question?
Sir, I was asking if we can expect substitution through hyperbolic functions.
Yeah, we didn't really cover that. You mean hyperbolic cosine and hyperbolic sine? Yeah, we didn't
So
really
we
cover
didn't
that.
cover yet.
Okay, Obed has a question?
Sir, is this our last class?
Yeah,
So on behalf of the class, I would like to thank you for all your efforts
okay, thank you.
and teaching us calculus. Hopefully, we can take more classes with you in the future.
Okay,
Yes, sir. Just take care. And thanks a lot for teaching us.
all right.
Yes,
Thank you,
Sir,
sir. Thank you,
it
sir.
was-
for
Thank
you, sir.
really teaching you.
Yes, sir. Thank you.
Thank you, sir.
it was an
Thank you,
honor
sir.
to be
Thank
taught
you.
by you. Thank you, sir.
Thank
Yes,
you so
sir.
much,
Thank you.
All right, so let's see.
I hope you make out
I
the
sent you
links.
the note for the link to the old exams, right? So if you go through those, there might be a few things because, you know, there's a little bit difference in the topics that are covered. So it may not exactly match up to your exam, but
Sir, when is the
Sir, one question.
yes.
But before that, Fatma, you can go if you want.
when is the exam?
Sorry, speak up. My connection here is not so good.
When is the exam? The final?
Oh, yeah, I don't remember. I think you get 2 weeks to study, right? So
No, sir. It's just one. Almost
just one. Okay.
Yeah.
22.
So, sir, the syllabus is going to be everything we did from the very first week till today.
Yeah, in principle, but usually what happens is that there's a slight difference between the sections, right?
Right.
Right.
Yes.
So I might have covered a section and someone else covers a section that I didn't cover or something like that. So
Right.
yeah, we have to give you a list, right?
Sure, sir.
Yeah.
We would be eagerly waiting for that.
Right.
Sir, we haven't done in integrals to infinity, so are they gonna come in the
No,
exam?
no, they won't.
All right, brilliant. Thank you.
So, sir, the syllabus that would be coming in a final exam would only be that every teacher has covered, and not what individual teachers have covered. Like you said, you have covered some topics that other teachers haven't.
Yeah,
So,
yeah. Like I said, it's possible that somebody has covered a topic that I haven't, and I've covered a topic that they haven't. So we have to take the intersection of what everyone has covered. That's what the test would be.
all right,
Okay.
sir. Thank you so much.
Certainly, everyone is going to cover at least up until integration by parts. I'm quite sure. So, you know. Okay.
Sir, just to be sure, like let's say we are gonna face some problems in revising stuff. So can you is it possible for you to like make some short session for problems and etc. Because especially when we are revising, definitely we will face some problems and confusions.
Yes, sir. Please.
If you actually come with if you're actually going to come with some problems yourself, then yeah, a problem session would, yeah, we could do that.
All right, sir.
Thank you, sir.
Okay. All right then.
Sir.
Yeah.
Sir, one last question. Sir, I just wanted to ask, where should we practice these concepts? I mean, from which book should you advise us to practice?
I think either Stewart or what's the other one?
Thomas and Finney.
Thomas and Finney.
So which one do you prefer?
I think they're both wretched.
All right, so if we could like go with Thomas and Finney and do
Yeah, I mean, I think
we will
Thomas
find,
and
right?
Finney covers at least everything that's sort of computational. I think Thomas and Finney covers that, right? But then Stewart will have a section on trigonometric substitution, which is just as good as Thomas and Finney's, right? So.
All right, so thanks a lot.
You know,
Thanks a lot.
I would look through the recitation, the problems in the recitations also.
Okay, sir. So the last question is that do you also teach calculus too?
Not so much these days, no.
And sir, about differential equations, which we have to off next semester?
Yeah, next semester I'm teaching a 4th year course. So yeah, I won't be doing that.
Thank you, sir. Thank
Okay.
you.
All right. Okay. So how about this? I will show up at our regular time on Tuesday at 6:30. Okay.
That would be perfect, sir. That would be perfect.
And if no one is logged in within 5 minutes, I'll assume that no one's interested, and I will log out.
No, sir. At least give us like 7 minutes, 7 to 10 minutes. Like
Yes,
there's
okay.
some connectivity issues, and
Okay.
But like, sir, we will definitely inform you about some problems through email.
Okay.
Yes, sir. Shah is absolutely right. At least 7 minutes.
All right. I will log in at 6:30 on Tuesday at our regular time. And if after some reasonable time no one has logged in, then I will assume that no one has come.
That sounds
Okay.
much
Okay.
nicer.
Fair enough. Fair enough.
Sir, is
Okay.
linear algebra easy?
Is linear algebra easy?
So
I don't
compared,
think so. I was thinking of opting up.
It's the most important. It's the most important undergraduate math course. So.
Really? Why?
Because everything useful that you do with math is actually linear algebra. Right?
Oh.
Pretty well everything
Okay.
we've done here could be done by, say, Wolfram alpha, right?
Hmm.
Except Wolfram alpha doesn't know when you can't do something. I mean, that's when the human gets involved, right? You can ask Wolfram alpha to do an integral that doesn't exist, and it will happily do it for you, right? Because it assumes that the human knows what he's talking about, right? So from that point of view, but as you go on, the applications of linear algebra is the structure within which you can understand the other stuff that you're doing. So
Okay.
conceptually, things make much more sense if your linear algebra is strong, right? So,
Okay.
4th year quantum mechanics is all linear algebra, at least the math part. So if you know the math, then you can use your brain to try and understand the physics.
right, sir.
Yeah.
Okay. Thank you, sir.
Okay, then. I'll see you on Tuesday.